Today I'm going to read What is Climate Change? This is a chapter book, the Who, What, Where, headquarters for history books. If you like, you can read along with me, or you can check out the book once I have read it to you. What is climate change? Copyright 2018. Okay, let's get started. What is climate change? In the Canadian Arctic, winter used to come early. By early November, temperatures dipped below zero. Snow covered the ground. Hudson Bay became covered in solid ice. Hundreds of polar bears lumbered onto the frozen water, making their way out to open sea. All winter long, they swam from ice to ice floe. They mated. They hunted and fished. There were plenty of ringed seals to eat. When summer finally came in August, the ice melted. The polar bears swam back to land. The males play fought. The females watched over their young cubs. Months passed. Polar bears lounged on tundra, still frozen ground, using light energy. They waited for cold weather. They waited to go out to sea again. Polar bears are strong, majestic creatures standing up to 9 feet tall and weighing up to 1,000 pounds. They are built for the cold. Their snow-white coat is thick, with a double layer of fur. Also, a layer of fat lies just under their skin, keeping them extra warm. For months, polar bears have to live off of this fat gained from winter feedings on the ice. When they're on land, they barely eat. In early November 2016, the polar bears were still on land. There was no sea ice on Hudson Bay. Weeks passed. By December, there was still barely any ice at all, so the polar bears had to wait longer to return to sea. Some paced back and forth along the shoreline. Others lay on the ground, not doing much at all. The warmer climate affected the polar bears in important ways. In the 1980s, Hudson Bay bears were bigger and rounder, well-fed. Recently, they've been losing weight and becoming weaker. That's because with fewer weeks on ice, their hunting season has become shorter. They have less food. In Hudson Bay, polar bears' numbers have dropped. The bears have fewer cubs, and not all cubs survive. In 2016, the water in the Hudson Bay didn't freeze until December 12th. That was very late. Sea ice is finally forming, one scientist reported. The polar bears are moving quickly offshore. Even on ice, however, the polar bears had a tougher time. There was more water between the floes. The polar bears were already weakened by long months on land, and yet they had to swim longer distances to get from place to hunt. Observers followed one female who had to swim 9 days straight to reach an ice floe. The Arctic, the polar bear's habitat, is changing. Temperatures have gone up about 3 degrees Celsius and 5.4 degrees Fahrenheit since the 1900s. The ice cover is shrinking too. In 2017, it was 30% smaller than it was 25 years earlier. And each year, the remaining ice cover is melting faster and faster. The fact is that our entire planet is getting warmer, not just the Arctic. Certain gases in the atmosphere, greenhouse gases, hold in heat, keep it from escaping into space. Higher temperatures bring changes in plant and animal life, in sources of food and water, in rainfall and snowfall, floods and droughts. Habitats around the world are at risk. It's all part of climate change. Chapter 1. Things are heating up. First of all, what is climate? Before you dress each day, do you check the climate to figure out what to wear? No, you check the weather. Weather changes often, sometimes in the space of a couple of hours. Climate doesn't. Climate is the weather over long periods of time. Scientists who study climate look at weather patterns. They need to measure temperature and precipitation, rainfall and snowfall. They'll look to see if there are changes over 30 years, 50 years, or even 100 years. By studying these long periods, they see whether conditions on Earth are changing. Scientists have taken measurements from weather stations around the world, in hot places and cold ones, and the average temperatures in all these places have gone up almost 2 degrees Fahrenheit since the 1880s. That may not sound like a big difference, but it is. Earth has been having fewer cold days and more warm days. There have been fewer record low temperatures and more record highs. Even freezing cold places are getting warmer, and not just in the Arctic. It's also happening in Antarctica, by the South Pole. Ice caps, glaciers, and ice sheets, all forms of land ice, are melting. When land ice melts, it runs into the sea. The additional water from the Arctic Ocean ends up flowing into all the oceans. This causes sea levels to rise around the world. On average, levels have risen 8 inches since the early 1900s and about 2 inches in 2000. Again, that doesn't seem like much, but these changes in the Arctic have an impact on weather patterns for the entire planet. It's like a teeny tiny spark that sets off a fire. In Alaska, coastal villages have already seen dramatic change. Homes are threatened by flooding and erosion. That's water wearing away the shoreline. Sea ice is melting. So is permafrost. So is permafrost, the permanently frozen soil just under the ground. The permafrost even feels different. It's springy, which causes houses to collapse into the water. The people of an island town called Schmismarth have voted to move their village. It will take years and much money to do it, but the people are ready. The land is going away, one man explained. What about places that are already hot? Higher temperatures are bringing changes in these areas too. Land is drying out. Water sources are dwindling. In Africa, Lake Chad sits on the edge of the Sahara Desert. Millions of people in Chad, Cameroon, Nigeria, Niger relied on the lake. once one of the largest in Africa for drinking water, fishing, and farming. But there is hardly any left. Since 1963, Lake Chad has lost nearly 90% of its water. It has shrunk because higher temperatures made the water evaporate at a faster pace. Overuse is another reason. After all, the lake provided food and water for so many. So how do climate scientists explain the global warming? It all starts with greenhouse gases in our atmosphere. Chapter 2, Something in the Air. Earth's atmosphere begins with the air surrounding the planet, and it stretches all the way out to space. It's about 60 miles above Earth. Our atmosphere is made up of layers of gas. Air has oxygen, of course. We need it to breathe. In fact, oxygen and other gas called nitrogen make up more than 99% of our atmosphere. That means only 1% of the atmosphere contains other gases. But it's those other gases that help control Earth's climate. We can't see any of these gases. We can't smell them or taste them. But they help heat Earth in a way that's similar to how a greenhouse keeps plants warm. That's why they're called greenhouse gases. In a greenhouse, sunlight streams through the glass, warming everything inside. Sunlight, a form of energy, streams through our atmosphere too. Most of the energy is absorbed by Earth's surface. It warms up everything, but some of this energy bounces back into space. The heat escapes. Greenhouse gases, however, can stop the heat from leaving. They trap it like a blanket traps your body heat to keep you warm at night. Without greenhouse gases, the planet would be a cold, lifeless place. For the last 10,000 years, these gases have helped keep Earth's temperature steady. An average global temperature that's in the high 50s Fahrenheit is perfect for animals and plants to grow. But Earth set new records for the highest ever global temperatures 3 years in a row, 2014, 2015, and 2016. And between 2001 and 2016, Earth had 16 of the 17 warmest years on record dating back to 1880. Also, we just saw a record high in Los Angeles County, Woodland Hills City, a couple of weeks ago, the end of our summer, temperatures reaching as high as 122 degrees in Woodland Hills, California. That is extremely high and extremely dangerous. Take note. If greenhouse gases have always been part of our atmosphere, why is Earth getting warmer now? It's because in recent years, greenhouse gas levels have risen, and one gas in particular is trapping more and more heat. It's called carbon dioxide, or CO2 for short. CO2 is made up of oxygen and one other element, carbon. An element is something so simple it can't be broken into smaller substances. Like oxygen, carbon is everywhere. It is in every form of life and in oceans, rocks, and soil. It moves from living things to the environment, then back to living things. How does this cycle work? People and animals breathe in oxygen and breathe out CO2. Plants and trees take in CO2 to grow and make food. In the process, they send out oxygen. It's like a delicate balancing act, but more CO2 in the air throws things off balance. It causes climate change. Of course, climate change isn't something that started only recently. It's happened again and again over the course of 1 billion of years. Chapter 3. Climate change through the ages. Chapter 3. Hot house, ice house, snowball. These three terms have all described Earth. At times, over the course of billions of years, the planet has been a hothouse with much warmer temperatures than we have now. It's been too warm for any glaciers or ice sheets to form. At other times, Earth has been an ice house, cold enough to create much larger glaciers and vaster ice sheets. The planet has even been a snowball Earth, covered almost completely with ice, slush, and snow. Learning about past climates. Scientists use different methods to figure out what the climate on Earth was like hundreds, thousands, and even millions of years ago. They examine tree rings, the growth bands that develop within tree trunks. The rings are wider in warm years and thinner in cold ones. They look at coral reefs that are millions of years old. Reefs have growth bands. Plus, they hold a form of oxygen that helps measure long ago ocean temperatures. They analyze ancient shells buried deep in the ocean that contain the same form of oxygen as coral does. They also drill deep into glacial ice cores to get samples of ancient ice. Tiny air bubbles trapped inside tell scientists about CO2 levels and temperature. In the beginning, 4.6 billion years ago, when Earth first formed, it was at its absolute hottest. The temperature was likely more than 3,600 Fahrenheit. Scientists are still learning about young Earth. First, it is supposed that a giant cloud of gas and dust spun through space. Rocks, dust, and gas collided. Gravity kept these bits and pieces together. The chunks grew larger and rounder, forming Earth and the other planets in our solar system. They all circled a much bigger glowing ball of gas, the sun. All those space collisions created great heat. Earth was too hot to have a solid surface. Instead, seas of melted rock covered the planet. Hundreds of millions of years passed. Earth cooled. The planet shifted a bit. It traveled around the sun at a slightly different angle. Because of this, Earth began to have seasons. Rain fell. Oceans formed. Earth cooled even more. Masses of land developed, along with volcanoes. Volcanoes and climate. Volcanoes release CO2 during eruptions and also from underground melted rock that seeps through cracks. Compared to millions of years ago, there is much less volcanic activity today. Yet erupting volcanoes still affect climate. Spewing ash forms a haze that blocks sunlight, causing a temporary cooling. The ash clears within a few years, but the volcano's CO2 and its warming effect last much longer. At that point, Earth was still very hot, most likely more than 400 Fahrenheit. Humans couldn't have survived. Also, the atmosphere had no oxygen. Still, one simple form of life did develop, a kind of bacteria living in oceans. The bacteria gave off oxygen, so Earth had the beginnings of breathable air, making way for different forms of life. Then the climate changed. A snowball Earth developed. Maybe all that new oxygen replaced greenhouse gases, cooling the planet. Or maybe there was a lull in volcanic activity, reducing CO2. Either way, scientists have found glacial rocks and other evidence of ice in every corner of the world, from the North Pole to the South Pole, and from South Asia to South America. Then, over more time, underwater volcanoes built up under the ice. Again, they spewed gases through cracks. They became more and more active. New forms of life developed around them. These creatures breathed in oxygen and released CO2. This caused Earth to thaw out over hundreds of millions of years. Two more deep freezes followed, ending about 550 million years ago. Was Earth finished changing? No. Land shifted and collided. New oceans formed. More volcanoes formed. More eruptions followed. The temperature climbed and climbed. About 540 million years ago, it may have reached an average global high of 90 Fahrenheit, about 30 degrees warmer than the average is today. Meanwhile, more life was developing, plants and trees and animals. With each shift in climate, new species developed. Others died out. Then came the age of the dinosaurs. It lasted until 66 million years ago. Earth had a warm, wet climate without any polar ice caps or glaciers. Forests grew close to both the North and South Poles. The CO2 level was 5 times greater than it is today. The dinosaur age ended with another major change in climate. One theory is that an asteroid or comet struck Earth. It moved great masses of land. It buried plants and animals. Wildfires raged, and soot and dust filled the air, blocking the sun for several years. Earth became cold and dark. The dinosaurs were wiped out. Slowly, the air cleared. Temperatures warmed and kept warming. By then, our continents were all in place. Small, mouse-like mammals evolved, and still the planet got warmer. Eventually, around 56 million years ago, Earth grew so hot that palm trees and crocodiles lived above the Arctic Circle. However, for the last 2 million years or so, from the time some of our earliest human ancestors walked the Earth to today, the climate on Earth has been in a pretty steady state. That does not mean there haven't been any further climate changes. It means the planet settled into natural climate cycles. A cycle is a series of events that repeat in the same order, and Earth has had regular cycles of warm and cold climates, with each cycle lasting about 100,000 years. When you hear the term Ice Age, you probably think of the most recent one, a cold, frozen time that ended about 12,000 years ago. Animals like the woolly mammoth and saber-toothed cats were alive. One well-known idea suggested that during this time, modern humans first traveled to North America, crossing the land bridge from what is now the region of Russia known as Siberia. This bridge was made possible by shallow seas, a consequence of low temperatures. However, new studies seem to disapprove this theory. Back then, average temperatures were 5 to 15 degrees Fahrenheit, colder than now. In some places, even summer felt like winter, and ice sheets reached all the way to what is now New York City. Humans wore layers and layers of animal fur to stay warm. But even ice ages have cold and warm climates. That sounds confusing, but it is true. A lot depends on Earth's orbit, the way it circles the sun. Sometimes during an ice age, the shape of Earth's orbit keeps it farther from the sun year-round, and the climate grows colder. These times are called glacial periods. When Earth's orbit changes shape, bringing it closer to the sun, the planet warms. These times are known as interglacial periods. Inter is from Latin and it means between. Believe it or not, right now we're in a warm interglacial period of an ice age. Scientists disagree exactly when the next cold glacial period might occur. But well-known climate expert Dr. Joseph Romm has written that he and the world's top scientists have confidence that right now the long-term trend for Earth, driven largely by changes in our orbit, should be a very slow cooling. Earth should be cooling, not warming the way it is. So something clearly seems off. Also, another weird thing is happening. In the past, each of the climate shifts took place slowly over millions of years. This time, everything is happening much quicker. It's almost like pressing a fast forward button. How do climate scientists explain all that?